So we take the 0 and 1 directions as special. We single out 0 and 1 directions. Let's say that A minus is equal to A0 minus A1. And we said A minus is equal to 0. This gauge breaks Lorentz invariance, but it's a price we are willing to pay for the simplicity that gives us. What is the simplicity that we get? You see, because we're doing Chern Simons theory, the only interaction between gauge fields is an A cube. Now, A cube is ultra local. So if any A at any point is 0, A cube is 0. And therefore, in this gauge, A cube just vanishes. So the Chern Simons part of the action becomes quadratic. Okay? We're also doing large N. So we're keeping only planar graphs. So planar graphs involving the exchange of gauge bosons where the gauge bosons don't interact with each other are very simple. Okay? So that's the main idea. So in order to understand scattering, we need to understand two things. We need to understand what is scattering, and then we need to understand the scattering. To understand what is scattering, we need to understand free propagation. So free propagation, basically, to find the exact propagator of the layer. Free propagation involves summing all these graphs. Graphs that we call rainbow graphs. I'm talking about the fermionic theory. The bosonic theory is slightly more complicated set of graphs because of self-interaction. No real additional complication. Okay, so in my drawing of diagrams for these theories, I will focus attention on the fermionic. Okay. Now, these graphs are very easily summed. They're very easily summed because you can show that the sum of all these graphs obeys a Schwinger-Dyson equation. Simply an equation of this form. An equation of the form sigma, the free energy, is equal. Let me write the equation diagrammatically first. Okay. So the free energy is simply equal to this diagram, where this arrow is the exact propagator. Okay? And these are all bare vertices. This is the bare gauge boson diagram. Okay? So it gives you an equation, an integral equation, which is schematically of the form sigma p is equal to 1 over q slash plus sigma of q times some Green's function for the gauge boson of p minus q. And then there are indices and so on that you have to worry about. Okay? So summing these graphs gives you an integral equation. And in a paper we wrote maybe 3 years ago now, two and a half, 3 years ago, with G and many other people, the purpose of that paper was to compute thermal partition functions. But along the way we needed to solve this equation. Actually in that paper also at finite temperature. A simple special case is 0 temperature. In that case, we solved this equation. We could find the solution of this integral equation exactly. Okay? It's not completely trivial. It's a non-linear integral equation, but it turns out to be the kind of integral equation that you can solve exactly with luck. Okay, so we could solve this integral equation exactly, and thereby compute the exact propagator. Okay, I'm not going to give you any details unless there are questions. Any details of the answers and so on. Just schematically indicate all the details in my papers, in our papers. Okay? So just by summing these diagrams exactly, turning them to Schwinger-Dyson equation, we find the exact propagator. No, quite simple. Conceptually quite simple. Okay? Answers are also quite simple. Okay? Not very complicated. Okay. Once we have the propagator in hand, now we need to understand scattering. So what do we have to do? We just have to sum all these diagrams. So it's really simple. At planar order, all you have to do is sum all these diagrams, except that everywhere you see a propagator, you should use the exact propagator. But we've already found the exact propagator, exactly in all orders in the Tuft coupling. So all you have to do is to sum all these graphs. Okay? All you have to do is sum all these graphs in order to get the exact test matrix. Okay. Now, summing these graphs can once again be turned into solving an integral equation. And so let me denote the full sum of these graphs by the renormalized exchange. Let me call it that. Okay, and the Schwinger-Dyson equation is simply that the full answer is equal to tree-level exchange plus tree-level times exact exchange. This equation sums all these graphs. So once again, summing these graphs is converted into solving an integral equation, this time a linear integral equation. Okay. Now, we were partially successful in our attempt to solve this linear integral equation. And let me explain, I have to explain that in more detail. Okay. Let me parameterize the momenta that go into this thing as follows. Let me call this P plus Q and K plus Q, and the momenta that come out like this as P and K. Okay? I've made some parameterization of momenta that implements momentum conservation. Okay? I should have said that there is an index structure to these graphs. The indices go like this in these graphs, the color indices. So whenever I draw these graphs, both momenta as well as color will flow in these lines. Okay, it's with this convention that these are leading order planar graphs. Okay, so what we want to do is to sum all these graphs with this momentum convention. Now, as I said, this is an integral equation, and let's try to understand in what sense it's an integral equation. You see, let's try to understand the structure of what's going on here. Suppose we've got some intermediate process with many gauge Bose-Einstein exchanges. This will have P plus Q and P. The momentum here will be some P prime plus Q and P prime. Momentum here will be some P double prime plus Q and P double prime. And so on until we get to K plus Q and K. What I wanted to emphasize is that in every intermediate step in this whole process, Q is fixed. Q is the center of mass momentum that runs through the graph and does not change. What goes on in different steps of the process is that you've got different values of this P and K. Okay? So it's like a matrix equation where the matrix indices are P and K. But Q is just a parameter in the equation. Okay? So you can look at this equation at different values of Q. That makes sense. Okay? Now, the point about this equation, and this was pointed out by Aharoni and collaborators, is that while this equation is quite complicated in general, it significantly simplifies when you choose Q plus minus is equal to 0. In that limit, by choosing Q plus minus equal to 0, we were able to completely solve this differential equation, this integral equation, both for the bosons and for the fermions. Okay? So now to get the S matrix from here, all we have to do is to take the answer that we get and put the particles on shell. But before doing that, we have to try to understand what this constraint of Q plus minus equal to 0, how this hampers us in what we actually want to find. Okay, there's a clear integral equation. Unfortunately, we were only able to solve it in this. It's nothing conceptual, it's a technical. As far as I know, it's nothing conceptual, it's a technical deficit. Okay, now, in order to understand what we lose by the fact that we could only solve at Q plus minus equal to 0, what we need to do is to understand the interpretation of Q plus minus equals 0 in the various different scattering processes.
Just choosing the SML mass frame?
Hang on. Yes, it's something like that. It depends on which are initial and which are final. So hang on to this. Suppose, as you suggested, the initial particles in the scattering processes were here, and the final particles were here. then Q is just the center of mass energy of the process. For that process, choosing Q plus minus equal to 0 is a disaster. Because in particular, it sets Q0 is equal to 0. So Q, the center of mass energy, is necessarily space-like. And so we can never put this process on shell. Okay? So for this process, this technical limitation basically throws the baby out with the bathwater. We can solve a problem that has, as far as this process is concerned, no direct physical interpretation. Of course, we don't expect, for instance, for duality, we don't expect these diagrams themselves to agree, right? That's trying to match gauge non-invariant correlation functions on both sides, which will not. It's only the S matrices that should. Okay? On the other hand, suppose you've got scattering processes like this, where these are initial and these are final. Then it's easy to check that Q is the momentum transfer from the initial, between the scatterers. Okay? And momentum transfer in the scattering of two equal mass particles is always space-like. Q plus minus equal to 0 sets Q to be some space-like momentum, namely in the Q3 direction. It's always possible to choose a frame so that the momentum transfer happens in the 3 direction. So if we assume that scattering is Lorentz invariant, which of course we're assuming, we lose no information. This technical limitation does not restrict our attention, does not inhibit us from computing the full S matrix in the process where these two are initial, or it turns out in the process where these two are initial, or these two are initial. Okay? So when you go through, when you look at this carefully, it turns out that what this allows us to do is to compute the full S matrix, but in 3 of the 4 channels that we were interested in. No prizes for guessing which one we weren't able to compute directly. That's of course the interesting one. That's somehow life, right? Okay, the one which is singlet exchange, okay, is the one that this technical limitation inhibited us from computing. But we could compute it in the other 3, and let me write down the answer. Okay, so apart from this piece, which was proportional lambda b times cot theta by 2, which was simply from tree-level Arnaud-Bohm exchange, the part that was non-trivial, the part that came from summing all these diagrams, was the following. Plus 4 pi I lambda b mod q times, so this whole thing multiplies this object here. 4 pi I lambda b mod q plus b4 plus minus 4 pi I lambda b mod q minus so plus b4 into half plus cb by iq over half minus half plus cb by iq to the power lambda b. Okay, and then the denominator is 4 pi I lambda b mod q plus b4. Okay, minus the same thing, minus 4 pi I lambda b mod q plus b4 into half plus cb by iq over minus half plus cb by iq to the power lambda. Where this q, mod q is simply this q3. For instance, if we look at this process, mod q would be square root of minus t for that process, the momentum transfer for that process. Okay, so this is an interesting, complicated function, of the scattering angle. Okay? And there's quite a rich analytic structure. This Q is the momentum transfer, raised to some power lambda b. Okay, it's something. So you can get an exact answer. Okay. Now, there are various things that I want to say about this answer. Okay, questions or comments before?
Those are subleading amplitudes, right? It's corresponding to that your gluons have a non-planar diagrams, right?
No. All this is clear. It was summing these graphs.
Aren't you just twist one of the fermion propagators such that the gluons can cross?
No, these are planar graphs because I can draw them on a plane. These, I could do the one by n counting for you if you want. These are all leading order graphs. These are all the same order in n as this guy.
Okay, but don't you get those 3 out of 4 non-drifting ones? Those are 1 of n diagrams?
No. In all channels, graphs contribute at leading order 1 over n. The thing I said was that those 3 out of 4 have trivial non-relativistic limits. Okay? And you can check that the non-relativistic limit of this answer is a very, very trivial thing, basically. Okay? But the full relativistic answer was not trivial. Okay? It was not some 1 over n counting. It was some Arno-Bohm business that told you that it had trivial non-relativistic limits. Okay. Good. The first thing I want to say about this thing is that it's a pretty complicated function of momentum. And so I've given you the answer for the bosons, by the way. B4 was the coupling. Okay? And one of the things you can check, there are 2 limits that are of interest. First, lambda b goes to 0. When lambda b goes to 0, you might think that the answer was going to 0 because it's lambda b here. But if you look carefully at the answer, the denominator also goes to 0. You know, so it's a 0 by 0. You have to expand out. You see, if lambda b is 0, this term is 1. This minus this is 0 if you ignore this term. But this term should be ignored because lambda b is 0. So the denominator is order lambda b. The numerator is order lambda b. Okay? So you have to expand this lambda b to first order, the denominator to first order lambda b. Expanding this gives you a logarithm. So it gives you an interesting non-analytic structure, and in fact can easily be checked to be what you would get from summing these graphs in 5 to the 4th theory. As should be, because when lambda b goes to 0, all that survives is the contact interaction for the scalars. So all that survives these graphs. So we reproduce these graphs. So we reproduce the right answer. So what I wanted to emphasize is that this answer has a non-trivial analytic structure even in the limit lambda b goes to 0. However, there is one value of lambda b where the analytic structure completely trivializes. This is lambda b equals 1. Because when lambda b equals 1, this is just this divided by this. And when you simplify this whole thing, and work it out, this whole thing simplifies to 8 pi Cp. Cp, by the way, is the pole mass of the bosons. It's different from the parameter m that appears in the Lagrangian, it's the pole mass. Okay? It just becomes this constant. So at lambda b equals 1, this whole analytic structure dramatically simplifies, and in fact exactly agrees with tree-level scattering, with this plus this term, exactly agrees with tree-level scattering of the fermions. Okay? Now, this agreement at tree level generalizes to the general case. So just like we had a formula for the bosons, we work out the formula for the fermions, I write it down for you, and then putting lambda goes to 1 minus lambda and the map, identifying the 2 pole masses, these 2 functions just completely agree with each other. Okay? So these S matrices that were computed completely distinctly on the bosonic and fermionic side just give you exactly the same answer. I emphasize that this agreement would not even have been sensible without taking the on-shell limit. Because for the fermions, we had more data in the off-shell propagators because we had psi of p as well as alpha, the fermionic index. Okay? But it's a particular property of 3-dimensional kinematics that on-shell, the momentum completely determines the polarization spin of a fermion. Just knowing whether you are dealing with the particle or the antiparticle. So there is as much data in on-shell scattering of fermions as bosons. So they could possibly have agreed, and they didn't agree. Okay? Now, yes?
Is it true that in a non-relativistic limit, there'll be no momentum exchanging scattering?
No, it's not true. But in these channels, certainly not in the singlet.
Let's see. I mean, maybe I thought that the particles just pass through each other, just pick up some phase, but you say that it's true.
No, because it's not true because they can wind around each other. It's the winding that gives you all the fun.
Okay.
Yeah. Okay. Other questions, comments? Okay. Now, this, you see, so far what I was doing was comparing scattering, where this is initial and this is final. And if you think through it, that turns into the scattering amplitude for particle-antiparticle scattering in the channel for adjoint exchange. Okay? Those two guys just exactly agreed with each other. On the other hand, now we can study particle-particle scattering. Okay, because we computed all. So for instance, where these are initial and these are final. So you remember that we have particle-particle scattering. Okay? Now, here we come, at first it's a bit confusing. Because while the diagrams for particle-particle scattering, the on-shell diagrams, just agree with each other between the bosons and the fermions, that does not sound like the statement that the answers agree with each other for the bosons and the fermions. Because in this case, we have both direct diagrams as well as exchange diagrams. Okay, where you hold, let's say, the two final states fixed, you could have P1 and P2 here, initial states, or P1 and P2 here as initial states. Now, the rules of quantum field theory tell us that the direct and the exchange diagrams should be added with a +1 for the bosons and with a -1 for the fermions. But the diagrams themselves were equal. So it looks like you're getting disagreement. Okay? But actually, there's a very interesting and nice resolution to this conundrum. And that is this. These signs turn out to do the following. What they turn out to do is to tell you that this for the bosonic theory is equal to this for the fermionic theory. And this for the fermionic theory is equal to this for the bosonic theory. Now, although we didn't think it through so carefully before we did the calculation, in retrospect, this is what you should have expected. Okay, there are two reasons for that. One technical and one physical. So let me give you the technical reason. The technical reason is that this duality that I'm talking about, okay, this duality that I've been talking about, has a very simple version that I didn't have the time to review for you in pure Chern Simons theory. It's called level rank duality. And this was one of these things about pure Chern Simons theory that was studied in great detail in the 1980s. And one of the things that was studied is, when you've got Wilson loops on one side of level rank duality, how does it match with Wilson loops on the other side? Turns out that it matches, but up to a level rank transposition of representations. And that level rank transposition of representations changes this representation to this representation. Okay? So, we're discovering the rules as we go along. We find that the S matrices on the two sides do agree, but only after you do the level rank transpositions of representations, which in retrospect is what you should have expected, because the duality we have is a level rank duality. Okay? There is a physical way of saying this. The physical way of saying this is the following. You see, suppose we've got two particles that are symmetric in their momentum labels, so all other quantum numbers. If the two particles are bosons, then they better also be symmetric in the color indices. But the same initial state data for fermions better then be anti-symmetric in the color indices, because one has to obey the Bose principle, the other the Fermi principle. So if you think about it physically, this is given that we're equating S matrices of bosons and fermions, this is the only thing that could have worked. Okay? So great. So in these three channels, we've got these S matrices really nicely agreed with each other. Okay. Fine. Now, let us look at what happens under under crossing symmetry. Alright. So we were able, as I've explained, in 3 of the 4 channels to just explicitly compute the S matrices. There's good evidence that what we're getting is not junk, because the 2 sides are agreeing so well. Okay, it's agreeing with every limit that it should and so on. It doesn't look like junk. Okay. Now, we had initially thought when we started this project that we can only solve 3 of the 4 channels, but we get the 4th one by crossing, so we won't lose any information. Okay? So what we did was to take these S matrices and continue by crossing symmetry to get a prediction for the S matrix for singlet exchange. And then we did consistency checks in that equation, on that thing. Okay? Now, already there's something very uncomfortable. You see, you remember that we had argued on general grounds and seen explicitly in the non-relativistic limit that the S matrix in the S channel, in this singlet exchange channel, must have this piece which is 1 minus cos pi lambda times delta of theta. Clearly that will never come from analytically continuing something like this. Analytically continuing anything analytic to this is not analytic. Okay, so fine, but maybe you could hope to have got everything else. So there's already some tension with analytic continuation here, the principle of analytic continuation. But let's proceed anyway. So what we did was to just analytically continue the answers that we got here to the S channel. So we got an S trial singlet. And then we checked this. The first thing we did was to check whether it obeyed the non-relativistic limit. Okay? Does it correctly reproduce the right non-relativistic limit? And the answer is not quite, but it does if you multiply this answer by sine pi lambda by pi lambda and add this term by hand. So S naive plus 1 minus cos pi lambda delta of theta. If you analytically continue, just for some reason, which we'll turn to in a minute, add this factor by hand, and then add this additional piece, then it has the right non-relativistic limit. As you perhaps saw yesterday, the non-relativistic limit, including these contact interactions, which we've included here, was quite an involved thing. Okay, so the match with the non-relativistic limit was not a trivial thing. Okay, okay, fine. But now, once we had this factor is just fixed by matching with the non-relativistic limit. Now there is a consistency check. The consistency check is unitarity. Okay, and this guess magnificently passes the unitarity check. Okay, in a highly non-trivial way. Okay, it's a highly complicated non-linear equation, which is very hard to satisfy if you just try to find a solution of it. Okay, if you just try to guess some functional solution of it, and it passes this check in a highly non-trivial way. Okay, so the fact that these two things come together, namely that this one simple factor multiplying the analytic continuation plus this delta makes the answer satisfy both unitarity as well as the non-relativistic limit, made us believe that this was the right answer in the S channel, and this is what we've conjectured in our paper. We've conjectured in our paper that the answer in the S channel is this. The S channel means singlet exchange channel is this. Okay, this is the answer according to our conjecture for scattering amplitudes for singlet exchange. Full non-relativistic answer. Okay. Now, in the last, I take 5 minutes before I start. Okay, right. In the last 5 minutes, I'm going to give you additional information that will help you make up your mind about, whether you believe what I'm saying or not. Okay. This factor here is very odd, but it's a factor that we've